Hi students, and welcome to the first presentation for the electricity module. In this particular presentation we'll be covering concepts of charge and current. So the main thing that we'll be looking at is applying the formula for current, which is the charge divided by the time, and we'll just look at some basic concepts about charge which you may remember from year 9. The first thing I think we should be talking about is the atom. Now, you remember from nuclear physics that we've just covered that the atom contains three main components. You have the proton and the neutron, which sit in the middle of the atom, called the nucleus, and then surrounding the nucleus you have the electron. Now, something that I'm sure you're aware of now is that the proton is positively charged, the neutron is neutral, which means it has no charge, and the electrons are negatively charged. And we're going to be looking more about charges in a moment. But effectively, if you have an atom that is neutral, then it means that you have the same number of protons as you do electrons. So if you look at an overall substance, so an object, if an object has more electrons than it does protons, then it's going to be negatively charged because electrons are negative. And if it has more protons than electrons, then it's going to be positively charged because of the protons, and the neutrons don't matter. So the core of this presentation is about charge. So something can be positively charged or it could be negatively charged. Now, if it's positively charged, then it will repel other positive charged objects. And if it's negatively charged, it will repel other negatively charged objects. But if you bring a positive charge close to a negative charge, then what you'll find is those objects will attract one another. So the main point here is that opposite charges will attract one another and like charges repel. A really good way to illustrate the charges is when we talk about static electricity. And when we have static electricity, what we've got is say, an object A and an object B. And if you have object A with more positive charge and object B is negatively charged, then those two objects will be they'll be attracted to one another. Now, the static electricity usually comes from the triboelectric effect, and this is where you have, say, two objects that are neutral. So I'll call this object C and D. And then when they come into contact with one another, if they're a different substance and they come into contact with one another and then they leave one another, then one object actually takes more of the electrons than the other object. So if you pull them apart, so the example of this could be sort of sliding down a slide, like in this example, or it could be when you're rubbing a glass rod with some fur. And when that happens, what you end up with is more electrons on one side, and that means you have an object that's more positively charged and an object that's more negatively charged, and once those objects come away from each other, they will have this attraction. And another example of this is if you're at home, if you get some Glad wrap and you unroll that wrap, what you'll find is that it will start sticking to itself for the same reason. So digging deeper into the concept of charge, we can actually quantify charge, and we can talk about how much charge something has, not just whether it's positive or whether it's negative. So we know that a proton has a positive charge, and we know that an electron has a negative charge, but how much? And that's where we have the concept of the elementary charge. The elementary charge is the smallest charge found in nature. So the elementary charge in this case would represent the charge of one proton or the negative charge of one electron. So essentially what we have is the elementary charge being the charge of one proton to be 1.6 times 10 to the negative 19 coulombs. So for an electron, it'll be the negative of that elementary charge. So we sometimes write it as negative 1.6 times 10 to the negative 19 coulombs. And that represents the amount of charge of just one electron. And now that we can quantify how much charge something has, we can go a little bit further and talk about how much force one charge will exert on another charge. Now, this formula is now in the year 12 curriculum, but now is a fantastic time just to quickly introduce it. And this tells us that the force between two particles would be equal to a constant multiplied by the product of both of those charges. And what that means is if you double the amount of either of the charges, then what you're going to be doing is doubling the force between those charges. And more importantly, this part here tells us, with the range between the charges being inversely proportional, that if you increase the distance between charges, the force between them will decrease as well, and that's what you'd expect. So when you separate these charged objects, the force between them decreases. But importantly, the amount that it decreases by is an inverse square relationship. So that if you double the distance between two charges, what you'll do is you'll reduce the force between them by a factor of 4. So now that we've spoken about charge, and we know that an object can have a certain amount of charge, and we know that electrons exhibit some charge, what role do charges play in electricity? Now, there's a couple of words that I just want to talk about first, and the first of these is a conductor. Now, a conductor is a material that allows electrons to move freely through it. So if you have a look at this diagram here, you can see that although the total number of protons is the same as the number of electrons at all times, this conductor is allowing the electrons to move from one atom to the next or flow through the material. And this allows essentially the transfer of charge despite it being a neutral material. Now, if an object can't do this, so it's holding very tightly onto its electrons, then we'll call that an insulator because the electrons can't flow freely through that material. And then you've got another type of material called a semiconductor. And a semiconductor is a little bit more complicated. It can conduct electricity. It does allow charge to flow through it sometimes. So it might be that it only allows charge to flow in one direction, for example. So when you have a flow of charge, we call that a current, and we talk about the flow of the positive charge. Importantly, I just want to say now that when you have a flow of positive charge, the positive charged particles aren't actually the things flowing, it's the electrons that are moving. So the flow of charge, or the flow of positive charge, is the opposite to the flow of the electrons. And you can see that in this diagram down the bottom here. The positive charge is not moving, but the electrons are, because they can, because that's the feature of electricity that makes it so wonderful. And we'll talk more about conventional current and electrons in another slide. But to have this current flow, you need to have an electric field, so you need to have a reason for them to move, so a force, for example, that's going to make these charges want to move in this direction, or you're basically a force that attracts those electrons from one side to the other. And you're also going to need some charges which can move freely. And when you have the charges that can move freely and you have a field that they can move through, then what you'll have is charges moving, which creates a current. And what we say, if we want to quantify that, is we say that electric current is the amount of charge passing a certain point in a given time interval. So we say current with the symbol I is equal to the amount of charge divided by the time. And if you have it all in SI units, the current is measured in amps, the charge is measured in coulombs, which we've already spoken about, and the time is measured in seconds. So just going a little bit further on that and talking about those units. So current, we say, is measured in amps, and 1 amp is equal to 1 coulomb per second. Now, if you wanted to then figure out how many electrons that was per second, well, you know how much charge one electron has. So if you know how much charge is passing through your circuit in any given time, you can actually figure out how many electrons are moving through a circuit per second if you know the current. One thing that trips a few people up is the symbol for current is I, and that means current. And current is measured in amps or amperes, which is given by A. So current could be 20.0 amps, and you'd write it like that. I is equal to 20A, A for amps. It's a little bit funny, but you'll get used to it. So let's get some questions done. Let's start with something really simple. You know that the current is equal to the amount of charge moving through the circuit divided by the time in seconds. See if you can answer this question. If 1.2 times 10 to the 4 coulombs of charge flows through a conductor in 1 hour, what is the electric current? So pause it now, have a go, and I'll see you on the other side. Okay, so with this question, what you want to do is start with the original formula, that the current is equal to the amount of charge passing through the circuit divided by time, and that's going to be equal to 1.2 times 10 to the 4 coulombs divided by time. Now time, if you want to get the current in amps, needs to be in seconds. So you have 1 hour, you multiply it by 60 to get it in minutes, and then you multiply it by 60 again to get it in seconds, and what you should end up with is 3.3 amps. Okay, now for another example, a current of 0.5 amp flows for 10 minutes. calculate the number of coulombs of charge that pass through a given point. So if you start with that equation again, if I equals Q1T, you will need to rearrange it, but you should be able to solve it. Have a go. Okay, so starting with that equation, I equals Q over T, you'd rearrange that to have Q is equal to IT, because the unknown is the charge. So you know the current, that's 0.5 amps, and you know the time is 10 minutes, but again, that's in minutes, so to get it in seconds, you need to multiply that by 60, and if you did that, what you should end up with is 300 coulombs. And by this point, you're probably realizing that these questions are fairly easy. And now try this question. It's a little bit trickier, nothing too serious. If you have 5 times 10 to the 18 electrons passing a point every second, what is the current? Give that a go. So again, if you just start with the equation, current is equal to the charge passing through divided by time. Okay, so how much charge is passing through? The charge passing through, we know it's 5 times 10 to the 18 electrons. What we need to do is we need to multiply that by the charge of an electron, 1.6 times 10 to the negative 19. Now, again, you could use negative if you like, but we're just giving a scalar value here, so I'm not particularly fussed. And you divide it by time. In this case, it's going to be 1 because it's passing through every second. So the current is going to end up being 0.8 amps. Okay, there's a couple of concepts that I want to talk about now. The first of these is conventional current, and I sort of alluded to this at the start of the presentation. The positive charge itself, which means the protons, they are not moving. Instead, what's happening is the electrons are moving, and the idea of conventional current being the flow of charge is left over from olden times. So to sort of help illustrate that, if I was to sort of draw a diagram of a circuit, so if I have this sort of circuit here, and I have a positive end of the battery and a negative end of the battery. So the way we typically think of things is that the charge is moving from the positive end to the negative end, and that's fine, and it does move from the positive end to the negative end, but the positively charged particles aren't the objects that are moving. Instead, it's the negatively charged objects. It's the electrons that are moving from the negative end to the positive end, and because of that, we consider the positive charge as moving anticlockwise. And that's where you end up with this diagram right here, which sort of shows us that the flow of electrons is the opposite to the flow of the positive charge, which means the current is opposite to the flow of the electrons. Okay, so I'm going to demonstrate current using a very simple circuit. So the first component I'm going to use is this battery. So this battery is the D-cell battery, and it's got a positive end, it's got a negative end, and I've put it here so it's easily accessible in this holder, so I can access the terminals using banana plugs. And then I'm going to be using a light bulb here. So the light bulb is an energy converter, and when current goes through the light bulb, it actually it lights up. And a light bulb in general just looks like that. And again, I'm just putting it in this block, which allows me to access the terminals, so positive and negative. Now it is a light bulb, which means that the current can flow in either direction. So to connect the circuit, I'm going to be using these banana plugs, and you can see now I'm going to have the positive charge running through this wire, and then it'll be entering the light bulb. Now I need to complete the circuit by allowing the current to run back to the battery. That one, and when I connect this up, what you see is that the light bulb has lit up, and the positive charge flows from the battery's positive end through the circuit and then returns to the negative end. But in reality, remember, it's not the positive charge, positively charged particles that are moving, it's the electrons, and they're actually starting at the negative end and they're flowing in a clockwise direction here. And if I wanted to figure out exactly how much current is moving in this circuit, I can use what's called an ammeter. So this is an ammeter here. Now, if I want the ammeter to figure out how much current or charge is passing through the circuit every second, what I can do is I can get the ammeter or connect the ammeter so that it intercepts the current going through it. So it starts at the battery here, comes around, goes into the light bulb, and then comes out of the light bulb, and then it goes into the ammeter, which effectively starts counting the electrons. So I've plugged it in again, and you can see that the ammeter isn't interfering with the circuit. It's still allowing the current to go through it. The ammeter is not even on, but you can see the light bulb is on. So as soon as I turn the ammeter on, you can see now I've been given a current reading. So it's telling me that 0.29 amps of current is running through this circuit. So what that means is 0.29 coulombs of charge is passing through the light bulb, passing through this wire, passing through the entire circuit every second. And there's a demonstration on current. And another concept you probably need to start thinking about is the idea of drift velocity. So we have this idea in our head that the electron in a conductor will just sort of migrate to the side of the conductor that it needs to go. But that's not how it works at all, because a conductor still has lots of protons and neutrons and stuff in there. So when the electrons want to move through it, it's going to encounter some problems. So what we say is that the electron has a drift velocity, which is the average velocity of this charge as it moves. And that drift velocity is an average because the electron is not moving consistently in one direction. As you can see in this diagram here, it's sort of bouncing all over the place. With this animation at the bottom, it's really cool. It demonstrates that the electrons are actually sort of bumping around on each other and also on the atoms themselves. And that shows us that if we actually cool down the substance, so if we cool down a wire, then the atoms aren't vibrating as much, which means they probably won't collide with electrons, or electrons won't collide with them as they migrate through the material. So this tells us that as the electron moves through a cooler wire, it will be met with less resistance, and we'll cover the concept of resistance later on. But this explains to us why superconductors, for example, work so well when the material is cooler. And that's it for this presentation. If you just want to make sure you understand the concepts of charge and current and the equations, you should be good to go. And then we'll move on to the next topic, which is looking at potential difference and voltage.